Section 17.5, factors that affect solubility. There's actually three factors that can affect whether something is soluble or less soluble. If you have a common ion, you can make something less soluble. We'll see that in a second. If you change the pH, so you either add more acid or base to a pH, you can, or to a solution, you can sometimes change the solubility of a salt. Or if you can make a complex ion, which is essentially not a, what's a complex ion? It's kind of where a molecule is hanging on to another molecule. They're not actually, it's not something new, but it's almost like connects or something where you're making a construction of various molecules together without making something new on itself. We'll look at that in a second. So the first one is solubility in the common ion effect. Now remember, if I'm making something, okay, so let's say in this case I've got magnesium fluoride and it's breaking apart into magnesium and fluorine. Well, I'm going this way, all right, I'm going to the right and I'm taking solid and dissolving it into ions. Well, if I dissolve in that water that's dissolving this ion, if I dissolve some fluoride to where I've got a big hump of fluoride, then essentially the left side becomes a dip, and this is going to go backwards and make less, so it's not going to have as much concentration of magnesium and fluorine, and so that's solubility, and the solubility will drop. So if you add an amount of a common ion, okay, to what you are doing, so if I'm making fluoride as one of my products, and I add some fluoride with a salt, say in this case sodium fluoride, then it's going to drive it back to the left, and by driving it back to the left, it's less soluble than it was. Okay, so here's an example. If I've got one of these magnesiums and two of the fluorines, so that's magnesium and fluoride, okay, and so for every mole of magnesium fluoride, I'm going to get 1 mole of magnesium, that's X. For every X, I've got 1X, and this becomes 2X. Well then, and I add some molarity of the fluoride, so this becomes bigger. Then when I do the molar solubility, I am going to essentially make this number bigger. Now it's a minus number, it's a negative number, and since it's bigger, it's actually less soluble than it used to be. Okay, so here's what it would be normally. 2.6 times 10 to the negative 4. So it's still very, not very soluble. But if I add a little bit of common ion, so add a little more fluoride, it's going to be even less soluble than it was. Okay, so let's say that there's some kind of a poison that I don't want in my water system, something that will kill people or make people sick. If I can somehow reduce its solubility in the water, say in my well or in a public water system, then I am helping people not to be poisoned by the stuff that would naturally come in through pipes or through rocks or whatever that water is going through. So remember, this is Le Chatelier's. Le Chatelier is that if you can pile up something on the, in this case, right, it's going to drive it backwards, and by driving it backwards, I'm not making as much product, and in this case, my product is that it's dissolving, so it makes it less soluble. So here's a graph. If you dissolve something in pure water, the more of, in this case, fluoride that I add, the less soluble that the magnesium fluoride becomes. All right, we've got the second factor, and remember that the second factor is the pH of a solution. Okay, so if I change the pH, if I tweak the pH, I can change the solubility of something. Now this example, I've got a carbonate. Okay, so I have a carbonate, and as a carbonate, if I add that with an acid, this would be like limestone and an acid that bubbles. So this would be acid rain, say eating a tombstone away and you can't read the date anymore or something like that, or eroding a statue to where you can't see its nose or something like that. So the calcium will react with the acid to make a bicarbonate, and then you're going to have some acid that will run off with the water. So it's basically making some water, and that's essentially what acid rain is. Right? So if you're gonna do this and I change the pH, I'm gonna change the amount that I can make. Okay, so let's look at this. The pH of the solution is going to change the amount of acid that it's adding with. Okay, so the lower the pH, the more acid that I have, and the more acid I have, essentially I'm piling up acid on this side, and it's going to drive it over, and I'm going to make more product and dissolve the calcium carbonate more. Okay, so remember, as it's going from left to right, this is dissolving. So if I can add the acid by dropping the pH, then I'm moving this to the right, and more of this is going to dissolve. So the acid, remember, pH is lower, is more acidic. So the more acidic that the solution, the more the calcium will dissolve, the calcium carbonate. Conversely, if you were to decrease the acidity, okay, the less acidity that you would make the pH of that solution, the less hydronium that you've got, the less it's going to move to the right, and the lower that the solubility would be. The third one is called complex ions, and a complex ion is where you've got some kind of a molecule or an ion in the inside that's then somehow connected to others. It's not its own molecule. It's basically like magnets, little magnetic sections of things that can hold on to others. The best example I can give you of a complex ion is how that hemoglobin, which is an iron-based molecule, holds on to oxygen. So oxygen holds on to this hemoglobin. It meets it up in the lungs when you breathe in oxygen. It holds on to it, and that hemoglobin in the red blood cell will take it to the body cell, but then be able to give it away. See, if it were actually bound like rust, so that it would be part of that molecule, it wouldn't want to leave. And so instead of it becoming something new, it's almost like a truck that's holding a cargo. Okay, so that oxygen in the case of a hemoglobin would be held on to that in that complex. Then it goes to the cell, and then that oxygen can come out really easy. So it's almost like a holder or a cup that it's holding something rather than something new. So it's not strong bonds like ionic bonds or molecular bonds. It's almost just like holding on to something temporarily, then you can let it go. That's a complex. If you can make a complex, all right, then what'll happen is that whatever you've got goes away, and that's dissolving. All right, so here's some examples. Here's silver ion that is going to be complexing with an ammonia. Okay, so you have something, you have a silver and ammonia that's kind of in complex together. So it looks like a molecule, but really it's just kind of being held by these ammonias. So we're forming a complex. And so, believe it or not, you've got a new K called the formation constant, which is really just an equilibrium constant of making this complex. And you have a certain number based upon these complexes. You've got like one holding on, and then you end up with two holding on, and sometimes these complexes can be huge, where you have 8 molecules kind of holding on to something, or 10 molecules holding on to something. They're very three-dimensional. So since I'm making something, even though it's not really a new compound, it's kind of a big monster, I can still do a compound, or I can still do an equilibrium constant, and that's where they found this one, for example. So if I can form a complex, like this is a complex, okay? So I'm taking ammonias, I'm adding ammonias to the silver and making a complex out of it, then what's happening is I'm dissolving the silver to do it. Dissolving means it's not there at the end. So if I had a silver ion and I put it in water, silver is one of those things that just doesn't dissolve well in water. Silver and lead and mercury and a couple of these other ones that, remember, were always on the side of the pool and never on the inside of the pool. If I can make something, change the pH a little bit, so this is ammonia, which would be a base, I add this base and make a complex out of that base, then what I'm actually doing is dropping the amount of ammonia or silver, and so I'm dissolving it. All right, so changing the pH in order to make a complex is a great way to get rid of it. And if getting rid of it is dissolving it, and that's what I want to do, then that's great. I'll do anything in order to get rid of it. If this is a poison or something, silver, you don't want heavy metals in your water supply. If you're trying to clean your water so that the kindergarten kids in your town is not poisoned, then you will add things to that water in order to get rid of these metals and stuff like that. So water treatment is not just, it's just really important. You don't want your people to die tragically. So you do things to the water in order to clean it, and that cleaning it sometimes involves doing chemistry on it. So here's an example. Silver chloride, this is silver chloride in the bottom of this water. It's very insoluble, okay? But if I add some ammonia, what will happen is that the ammonia can be grabbed onto the silver and essentially be held by it. It's not something new, it's just kind of a construct. It's not a new molecule, it's kind of the ammonia being bound by this silver. That's what a complex ion is. It's still an ion at the end, but it's ions linking together and kind of holding on to each other somehow, kind of like little magnets holding on to magnets, because this is positives and negatives, so they're like little tiny ionic bonds, but not exactly, something close. All right, so if I can make a complex out of it, then the silver that I'm putting in, and like the silver chloride, dissolves. All right, and then you end up with chloride ion, so you're dissolving it. So by adding ammonia, that's what they've done. They've added some aqueous ammonia. All of this silver chloride dissolved. Even though, if you remember, chlorides were one of the little swimming kids in the swimming pool, and silver was one of your exceptions. So it's not soluble. But if I add a little bit of ammonia, suddenly it is soluble. Why? Because I'm making complexes out of it, and I'm dissolving it in order to make the complex, and that's what I wanted to do in the first place. So here it is. The more of this that I can make to make a complex out of it, the more soluble, or the concentration, as the higher the concentration of this becomes, the more silver in the silver chloride gets absorbed into this complex. That means that the silver chloride is going to dissolve. It's a way of dissolving something simply by making a complex ion out of it. All right, there are some ions that can be more soluble if you put them in strong acids, and more soluble if you put them in strong bases. And normally they're soluble for different reasons. Here's an example. If I add acid to this hydroxide, okay, remember by adding acid, the higher the acid, this acid base, the hydrogen and this becomes water. Okay, the more acid I have, I'm bumping up this side. That means it's going to drive it over, and I'm going to make more water. And by making more water, I'm dissolving the aluminum hydroxide. So this isn't a case where acid is dissolving it, but base is also dissolving it because I'm making a complex out of it. It just happens to work this way. This is called amphoteric. Amphoteric means if you add acid, it'll increase the solubility. If you add base, it'll also increase the solubility. There's different reasons for each of them, but you're still getting the job done. So there are some ions that if you make it more acidic, it'll get more dissolved, or if you make it more basic, it'll get more dissolved. Either way, pick one, it'll work. So in the case of this example, aluminum hydroxide, if I add more hydroxide, so I'm increasing the pH, I'm adding more hydroxide, I'm making a complex where I've got aluminum with some hydroxide ions here. It's a complex ion, and so it's getting rid of this aluminum. It's dissolving it. Evidently, this is soluble. See, it's aqueous, but this is solid, so it's dissolving it into the solution, and that's what I wanted to do. Here's an example of that amphoteric. If you've got something that is insoluble, and I increase in this case, hydroxide, because hydroxides make a complex ion out of it, they are soluble, but the original stuff was insoluble, it'll dissolve. And if that's what I'm trying to do, it could either, an acid will work in one direction, or a base will work in the other direction for different reasons. So you end up with a really cool graph. It's more soluble in acid, less soluble as it goes to neutral, and then more soluble in base, because these guys are forming complex ions, and this is simply an acid-base reaction. So amphoteric is kind of cool.